Welcome again to a new lecture on solar photovoltaics principles, technologies and materials. So, what we'll do is that we'll just have a quick recap of last lecture. So, in the last few lectures we have talked about monosilicon and polysilicon solar cells. Monosilicon are basically single crystal silicon solar cells, and these are polycrystalline. So, because of presence of defects, the polycrystalline efficiencies are a bit lower. So, in this case we have efficiencies of 25-26% efficiencies. In this case we have efficiency of 23% best efficiencies obtained. However, they are not too bad given that there is a significant cost differential between the two. So, polycrystalline ones are cheaper than single crystals, and then we looked at strategies to improve performance, which are basically also design criterias. So, first was to improve the optical light coupling, then we need to control the doping, electrode design, surface recombination reduction, use of anti-reflection coatings, and so on and so forth, and you can say here buried contacts. Okay. So, these are certain strategies which are used to improve the quality of both polycrystalline and monocrystalline silicon solar cells. The way it is done in two solar cells may be slightly different, but they are by and large similar. Now, we will look at a bit about the silicon manufacturing. How do you do silicon and silicon device manufacturing? So, to begin with, we talk about silicon manufacturing. Silicon is generally manufactured in 3 steps. So, the first step is we have metallurgical grade silicon, which is very impure. This metallurgical grade silicon is then converted into semiconductor grade silicon, which is essentially, you can say, polysilicon. Okay. And then we have third one called as single crystal silicon. So, we obviously cannot use this for semiconductors, but we can use these two for semiconductor processing. Semiconductor grade silicon, that is polycrystalline silicon, is used for polycrystalline silicon solar cells, and the single crystal silicon is used for monocrystalline silicon solar cells. So, there is an additional step that is used to convert the polycrystalline into single crystal silicon solar cell, which basically involves melting followed by resolidification to make single crystals. So, essentially it is about melting and resolidification, and this is about purification and deposition and purification. Okay. So, you have 2 steps, deposition, purification. So, metallurgical grade is complete no, but semiconductor grade and single crystal silicon both are used in practice. So, metallurgical grade silicon, how do you produce metallurgical grade silicon? First of all, so metallurgical grade silicon is basically made from, to begin with, you start with lumpy quartz. Quartz we know is nothing but SiO2, and essentially you made it react with carbon. Carbon is in the form of coal, or you can say coke, etc. Various forms of carbon is present. So, essentially you make SiO2 react with, in the solid form, react with carbon in the solid form, and this gives rise to silicon, that is liquid and which is in the gas form. This is a very energy intensive process because free energy formation of silicon oxide is extremely negative. So, thermodynamically this reaction is very energy intensive. So, it goes at very high temperatures. So, first you have to go to between about 1900 to 2000 degrees centigrade. Your silicon oxide in solid form reacts with silicon carbide in solid form to give you 3SiO in the gas form plus carbon monoxide in gas form. And then this SiO in gas form reacts with again silicon carbide in solid form, gives you 2Si liquid plus COG. This is a multi-step process, and below 1900 degrees centigrade the reactions that occur are this SiOG plus 2C in the solid form. This makes SiC solid plus COG, and then 2SiO gives rise to Si liquid plus SiO2 liquid. So, the liquid that you get after this processing is, first you go to 1900 to 2000, then below 1900 gradually, and then you obtain from this liquid silicon which is 97 to 99% pure, with impurities like iron is about 0.2 to 1%, aluminum is about 0.4 to 0.7%, then we have calcium which is 0.2 to 0.6%, and so on and so forth. There is a bit of titanium 0.1 to 0.2%, and then we have carbon 0.1 to 0.15%. There may be some other impurities also. This is what is the composition. This is complete no-no for semiconductor processing. This is very impure. So, what is done next is, next you do refining. Refining is always a energy intensive process, and this is used, refining is done by agents which react with the impurities. So, basically it is an oxidative process. So, essentially it is an oxidation of impurities. So, this is a very tricky process because you have to choose conditions which do not lead to oxidation of silicon, but the impurities. And remember, silicon has high affinity to react with oxygen. So, as a result it is not very easy. So, oxidation of impurities to form slag. Slag is nothing but the impurities, molten pool of impurities. So, essentially, but you cannot completely prevent the oxidation of silicon. There is always some oxidation of silicon that happens. So, as a result what happens is that you also add some SiO2 in this process. So, aluminum, calcium, magnesium, etc., they react with SiO2 to form Al2O3, CaO and MgO, and these make what we call as slag. And then of course you do, so essentially you are saying you have partial oxidation of silicon here. And then what happens is that you do casting and further refining. All right. So, it is a very tedious, energy intensive process. You have to go multiple stages of refining, and that is why silicon, sand is cheap, but silicon is not. So, a typical metallurgical grade silicon will consist of your aluminum. So, metallurgical grade silicon. So, this is where we have this rather purified metallurgical grade silicon. We have aluminum of the order of 1200 to 4000 ppm, boron of the order of 37 to 45, so all in ppm, phosphorus about 27 to 30, and then we have calcium, we have chromium, we have copper. Iron is relatively large, 1600 to 3000 ppm, and then we have manganese, we have moly, we have nickel, we have titanium, we have vanadium, we have zirconium, and all these are less than about 100 ppm, okay, all of them except iron. Okay. So, these are less than 100 ppm typically, some of these may be 200 ppm or so, but generally about less than 100 ppm. So, this is the metallurgical grade silicon. This is very, very impure, not fit for semiconductor processing. So, what you do is that then you process this metallurgical grade silicon to purify this using other processes. So, the semiconductor grade silicon is made by so from this silicon that we obtain, we make first volatile silicon hydride SiH4, then we purify it, then we decompose this to elemental silicon, and then we go to byproducts. In the process we have, well, it is not a part of the process as such, but this is what happens. You have byproducts which are recycled into these stages. Okay. So essentially you first make metallurgical grade silicon, then convert the metallurgical grade silicon into these silicon compounds like silicon hydride, because remember, no matter how much liquid processing you do, you can't make very pure silicon. So, you have to take it to vapor stage where only silicon is able to come out, rest all does not come out. So, after you have done primary refining using the metallurgy processes, you have to go to the processes which are more of deposition processes than liquid based processes. So, in this case there are three processes that we generally use, but generally the Siemens process is the one. So, Siemens process is the first process that is used to make silicon, and then we have union carbide process, Siemens process accounts for about 60% silicon in the world, and union carbide process accounts for about 15% silicon production, and then third is what we call as ethyl corporation process, which is about again 15% or so. So, let us see, we will not go into all of these, we will just look at the Siemens process. Okay. So, Siemens process so what happens in Siemens process is you have basically we first make trichlorosilane, okay, trichlorosilane. This is thermally decomposed at 1100 degree centigrade on a heated silicon rod, okay, inside a decomposition chamber, and then it gives rise to what we call as silicon SiCl4, and this SiCl4 is then converted into silicon. So, the way we go about it is we have this chamber, which is a dome shaped chamber, right. Within these so we have these silicon rods like these, these are silicon rods, okay, prefabricated silicon rods. So these are, you can say, polysilicon rods, and then of course you have some cooling medium here, vent, sorry, cooling. And then what we have here is, we have this, these are electrical contacts, to heat these rods to high temperatures. So temperatures are about 1100 degrees centigrade, and then through this thing we pour in what we call as, we put in SiHCl3, which is the silicon trichlorosilane, and hydrogen, and then somewhere here we also have a outlet for other gases like SiCl4, etc. they come out, okay. So and then the coolant goes out from this side, because we also have to keep the chamber cool, otherwise. So it's a double body chamber like this. So this is a double wall chamber. So keep the coolant, so this has coolant flowing, so coolant flows and keeps this cool, okay. So this is coolant. Now in this, the reactions that happen are 2 of SiHCl3 makes SiCl4 plus silicon plus 2HCl. So it's not a very friendly reaction. You can see that the things that are forming are not very benign, and this happens in multiple stages. So you have 2 SiHCl3 goes to SiH2Cl2 plus SiCl4, then SiH2Cl2 forms Si plus 2HCl, and then this hydrogen also reacts with HSiCl3. You can see I have replaced it here. So this becomes Si plus 3HCl, and HCl plus SiHCl3, they make SiCl4 plus H2. So you can say this is SiHCl3, sorry. So these are multiple reactions that occur in this process to give you eventually the silicon. This is a very energy consuming process. It's a slow process, it's an energy consuming process, and this is what is used for making silicon in the industry. Over 60% silicon is made worldwide using this process. So this results in the formation of silicon, which is quite pure semiconductor grade silicon, and basically the silicon which comes here, it gets deposited on these rods, okay, and these rods become thicker and thicker and thicker and thicker, and then you of course take them out, cut them, make wafers. That is what you do, okay. And so there is a whole scheme of this process. I will not go into details of that process. So this is what is the basics of making silicon, okay. And then we make silicon ingot from. So now if you want to make silicon single crystal, you make silicon ingots. So silicon ingots are made by melting silicon, okay. So whatever polysilicon you make, that's pure, then you melt it. After melting, you make ingot. It's casted, and once it's casted, it's a big ingot of. So after casting, it becomes like a big ingot, okay. And generally, it's like it has a little nozzle shaped nose on the two sides. So this is a big ingot. And these ingots are then, if you want to make single crystal silicon, they are recasted and resolidified. So you can make a polycrystalline ingot, or you need to re-solidify to make single crystal silicon. First process is called as Czochralski, Czochralski, and then second method is called as float zone. So, principles of solidification and impurity segregation are used to make highly pure and highly single crystalline, highly defect free silicon. So, essentially what happens here is in these two methods. So, in using these two methods, basically these are slow and controlled solidification, okay, methods which give rise to formation of single crystal silicon. So, you can read them through the books, Czochralski and float zone method. They are basically solidification and methods to make single crystal silicon. So, once you make these single crystal ingots, they are like this. So, they are of the diameter about 200 to 300 millimeter. These are ingots, and they are quite tall. They could be, I think about a meter long or so. Out of these, you need to make wafers. So, what you do is that you do wire sawing of these to make wafers. Okay. So, these are cut into small pieces to make wafers. So, this gives rise to wafers. Each wafer is of the order of 0.3 to 0.4 mm thick. When you make these wafers, because of sawing, you create silicon dust. So, silicon is wasted, lot of silicon is wasted during sawing, and sawing also leads to damage to the surface, right. Sawing also leads to damage to the surface, so wasted as well as surface damage. So, to make a device quality silicon, you again need to do lot of processing. So, this is for example, so initially the silicon is more or less p type to begin with, the dopants that happen to be there. So, essentially you have a silicon, this is let us say p silicon to begin with, it has lot of surface damage. So, this is damaged silicon wafer. This is then chemically treated, chemically etched on the surface, so that you get a nice clean surface. So, the surface is cleaned by etching to remove the rough material of the surface, and then after that you do texture etching, texture formation. This is to improve the light coupling. So, you create this kind of, so this is called as controlled etching, use of right etchant, so that you have right plane in the wafer which is etched. So, you create this kind of surface etching, and then you do the diffusion of phosphorus diffusion to make N type silicon on top. So, this is P type to begin with, the phosphorus comes from top. So, gases containing phosphorus come. So, for example, you can have gases like I do not know, POCl3, okay. So, POCl3 will come from top, phosphorus will diffuse. So, this region will make N silicon, this will remain as P silicon, okay. And then you, after you have done that, you chop off the edges a little bit. So, you can do what we call as edge isolation, because there will be some damage on the edges as well. So, you chop off the edges to make little smaller, After you have done edge isolation, we do the process called as ARC deposition. So, then you do ARC deposition on top of it. So, anti-reflection coating is deposited, and then we make a front contact which can be screen printed, and then we make what we call as back contact. So, this is sort of the you can say a procedure for making a silicon solar cell, and then you do firing. So, back contact printing you can say here, firing to just make sure that the contact stabilizes and it solidifies, and after that you do testing, encapsulation and testing, encapsulation and testing. Okay. So, this is the complete flow chart of the way silicon is made. So, if you have seen in one of the earlier lectures that what does it look like after once you make the contacts. On the back side, of course, you will have completely printed surface with aluminum all over the place. The front side looks like this. So, these are screen printed contacts, printed silver contacts on top. So, you have a thicker contact on top to connect all of these layers together, but these are the fine contacts running across the length or breadth of silicon. Okay. So, this is what is silicon manufacturing all about. So, just to summarize for silicon, we have looked at silicon solar cells in quite detail for both mono and poly. We also looked at design strategies to improve the silicon quality, to improve the performance. We also looked at the manufacturing in some detail, not very detailed, but just a schema, just a flow chart of how silicon solar cell is made. Currently, silicon is the dominant technology in the market. With single crystal silicon having about more than 25% efficiency and polysilicon having efficiency of more than 22%. The modules are of about 19-20%, and in this case the modules would be about 15-16%. This is for modules. Let me check the numbers. So, yeah, modules would be lower than what you get. So, about 20% you will get for single crystal, about 15-16, maybe 17% for the, you can say 15 to 18% for the polysilicon. And these two are the dominant technologies right now in the world. So, what we will do in the next lecture is we will talk about little bit about gallium arsenide, just to look at the basic structure of gallium arsenide solar cell, and then we move on to second generation technologies, which is thin film solar cells. Thank you.